A lone jogger crosses Grantchester Meadows in the early morning fog. He trips because he's not paying attention to the path and has forgotten whether he turned the oven off. Again. A faint sunrise lights the scene. Not trending on ArtStation. Dream. Intriguing. That's not too bad, you know. This is the output of SDXL 0.9. A couple of weeks ago, Stability announced the existence of SDXL 0.9, describing it as a leap forward in AI image generation. Today, they released a technical report for SDXL that describes the techniques they used to improve the image generation quality. In this video, I'll walk through the key ideas in the technical report. The samples look nice. Look at this alligator having a drink, so smartly dressed and ready for business. Although there's something physically odd about this cup floating on a non-existent table, still, this crocodilian doesn't look bothered. Clearly, a major financial transaction is about to go down. In this report, the authors unveil SDXL, a drastically improved version of Stable Diffusion. Here's the basic architecture. Starting from the noise and a prompt, the base model produces an unrefined latent of the same size. Then the refiner improves it. Then a VAE decoder maps it to the final image. In this case, 1024 by 1024 pixels. But is it really drastically improved? Yes, according to their user preference study. Compared to Stable Diffusion 1.5 and Stable Diffusion 2.1, the SDXL base model is significantly preferred. Adding in the refiner stage makes things better still. There aren't many details in the report about how this study was conducted, but still, these bars certainly look much taller. Let's look at the key ingredients that drove these performance gains. The first relates to architecture and scale. Compared to previous Stable Diffusion models that used 860 million or 865 million parameters in their units, SDXL cranks this up to 2.6 billion with a slightly different configuration of transformer blocks. SDXL also uses a more powerful pre-trained text encoder for text conditioning. They use OpenClip VIT Big G in combination with Clip VIT L, where they concatenate the penultimate text encoder outputs along the channel axis, and additionally condition the model on the pooled text embedding from the OpenClip model. Intriguing. The next ingredient is conditioning the model on image size. The motivation here is a problem with latent diffusion models. They require a minimal image size. That means that you have to discard all training images below a certain minimal resolution, which was done in Stable Diffusion 1.4 and 1.5, and which is clearly excruciating to us deep learners who love having as much data as possible. In this case, using a threshold of 256 pixels would mean that 39% of the data would be discarded. That's a lot of data. Sad times. Our other option is to upscale images that are too small, but that creates upsampling artifacts. The trick here is to simply tell the model what the image size is by passing it as additional conditioning information. A tuple csize containing the original height and width of the image. Then, at inference time, a user can set the desired apparent resolution of the image via this size conditioning. If we generate 512 by 512 images and condition on an image size of 64 by 64, we get something blurry. But it gets sharper if we ask for 128 by 128, sharper again for 256 by 236. I'm going to guess this should say 256. And nice and crisp for 512 by 512. Experiments on class conditional ImageNet suggest that this size conditioning really does help performance. The second trick is similar, conditioning the model on cropping parameters. The motivation here is that previous Stable Diffusion models sometimes produce images that are badly cropped. Look at this cat. Where are his ears? The problem here is that random cropping used during data augmentation can leak into the generated samples, and we don't want that. To fix it, during training, we let the model condition on the crop coordinates ctop and cleft, which define the cropped box location. During inference, we can now specify crop parameters like 0.256 to get an image cropped from the left, or 2560 to get an image cropped from the top. And most importantly, we can pass 00 to get an image that is not cropped from the top or the left. The next ingredient is multi-aspect training. This is pretty much what you'd think it is. Rather than just outputting square images, it allows the model to output landscape ratios, like 16:9, or portrait format screens. Again, this is done by passing to the model a tuple for the image size as conditioning, the target height and the target width. This multi-aspect training is done as a fine-tuning stage after pre-training the model at a fixed aspect ratio and resolution. The next piece of the puzzle is an improved autoencoder. This is achieved by retraining the same autoencoder architecture used for the original Stable Diffusion at a larger batch size, and additionally tracking the weights with an exponential moving average. Some experiments on Coco 2017 suggest that this does indeed yield gains. We now reach the point of putting everything together. There are 3 stages to training the base model. Training at 256 by 256 pixels, and a batch size of 2048 for 600,000 optimization steps, then training at 512 by 512 pixels for another 200,000 optimization steps. Then finally some multi-aspect training. After this training, they found that sometimes the base model produces blurry bits. These buildings are not super crisp, and neither are those ripples. Those are some sharper buildings. And look at those nice little waves. These improvements come from adding a refinement stage, which is a separate latent diffusion model in the same latent space that is specialized on high-quality, high-resolution data and uses the noising-denoising process as introduced by SDEdit on the samples from the base model. This is found to improve sample quality for detailed backgrounds and human faces. In this portrait, it improves this ear to this, and for this group photo, Refinement improves this face to this. In further experiments, the authors provide a comparison to Midjourney version 5.1. The comparison was against version 5.1, since that was the best version available at the time of the experiments. One important factor here for the user study that compared the two models is that the human annotators voted based on adherence to the prompt. So it may be that the images that won did not necessarily look good. Still, there is clearly some signal in this study. The results suggest that SDXL, represented here in blue, was slightly favoured over Midjourney v5.1, represented here in orange. The authors also say that preliminary testing indicates that the recently released Midjourney v5.2 has lower prompt comprehension than its predecessor, but the laborious process of generating multiple prompts hampers the speed of conducting broader tests. This may perhaps be an allusion to the long-running request for an API for Midjourney. If you want to conduct a large-scale comparison, you need to be prepared to spend some serious time on Discord. Let's look at limitations. There are hand issues, of course. This one has some slightly odd spacing between the fingers. Not sure what's going on there. And this is not a typical number of fingers. In my own experiments with the prompt, Samuel Albany furiously writes a YouTube script. I sometimes get some pretty wild things happening, not just with the hands, but also with the forearms. Clearly, I'm writing very furiously. Among other limitations regarding biases and concept bleeding, SDXL still encounters difficulties when rendering long, legible text. For the prompt, a green sign that says Very Deep Learning and is at the edge of the Grand Canyon, SDXL produces a sign that says Very Deep Lanting, Grand Koani. So still, a little room to improve here. That's it, we've reached the end. Thank you for listening. I hope you have a wonderful day.